Hello everyone, I am Dilruk Pereira, a PhD candidate at National University of Singapore. In this talk, I am going to discuss about how we can synthetically generate missing user preferences for cross-network recommendation purposes. And this talk is based on one of our recent works published in last year's WWW conference. As we are aware, there are overwhelming amounts of information available on today's web applications. If you look at platforms like YouTube, over 500 hours of YouTube videos are uploaded in just 1 minute. That means an average person would have to spend their entire lifetime trying to watch videos uploaded to YouTube in just 1 day. And in Snapchat, over 270,000 stories are uploaded in every minute, and the number keeps increasing. With this many information coming into these systems, we face the information overload problem, which means whenever a user logs into one of these systems, they cannot possibly go through all the available items to pick and choose the ones that they would like to interact with, because there are simply too many items available. And recommendation systems are considered as the generic solution to this information overload problem. Mainly, recommendation systems learn user preferences by observing their user profiles. Basically, these user profiles contain all the items users have previously interacted with and the ratings given to the items. Basically, the information about what they like and dislike. Once recommendation systems model user preferences based on their profiles, they automatically recommend a small subset of interesting and unseen items to users, so that the users do not have to do the filtering manually. And I'm sure every one of us here have been benefited from these recommendation systems. For example, on YouTube, you can see that they recommend personalized content according to our interests. And on Netflix also similarly, they recommend new movies based on the movies that we have previously watched. And even the thumbnails here are sometimes personalized just for you. And recommendation systems are not only beneficial for users or consumers like us, they are valuable for applications as well. For example, over 75% of movie views on Netflix are initiated by their recommendation system, and over 35% of Amazon sales are based on their recommendations. So it is very clear that recommendation systems provide mutual benefits for both users as well as applications. However, despite these effectivenesses, recommendation systems still suffer from certain limitations, and let's briefly look at them here. First, let's consider new users in an application. These users are newly registered to the application, so they don't have any interactions with any of the items available in the system. And that means user profiles for these users are basically empty, so the recommendation system cannot comprehend their preferences. This is known as the cold start problem, because the recommendation system does not have enough information to heat up the recommendation engine. And traditionally, these users are either considered as an average user and recommends a default set of items, or use whatever the minimum information given at the registration for recommendations. But these are not very effective ways of recommending items. And also, it is really vital to provide effective recommendations to these users, because it will influence their initial opinions towards these applications. And also, the new user base is quite high in popular applications. For example, applications like LinkedIn have millions of new users registering in every month. Then there are existing users who already have interactions with the items in the application. However, since there is very high item to user ratio, users cannot possibly interact with a large portion of the items, even if they would like to interact with these items. So the resulting sparse information on their preferences leads to low recommendation quality. This is known as the notorious data sparsity problem. And so it is very clear that we need to develop recommendation systems that are robust against these popular problems. One of the most effective ways of overcoming these problems is by using cross-network information of the users. Because nowadays, users are engaged with multiple different social networks simultaneously. For example, a user who watches interesting videos on YouTube may follow trending news articles on Twitter and share posts with his friends on Facebook. And all the interactions that he performs on these networks showcase his preferences from a diverse perspective. So if we can combine all these interactions together, we can create more complete user profiles containing information about his overall preferences from a diverse perspective. So that means for new users, we can directly use information about their preferences from other networks. So although we don't have preference information on a particular target network, we can get his information from other networks. And for existing users, although we have their preferences on a particular application, we can enrich or get more information about their preferences and get more comprehensive user preference profiles about these users. And so this is how cross-network recommendation systems solve the issues associated with conventional recommendation systems. And these are some of the results obtained by our previous studies, just to show how effective cross-network recommendation systems are. Here we use user interaction information from both Google Plus and Twitter to conduct YouTube recommendations. So both Google Plus and Twitter are source networks, and YouTube is the target network. Here we compare the cross-network recommendation results against conventional single network-based recommendation results. For new users, traditional recommendation systems are unable to provide recommendations because their user profiles are basically empty. But cross-network recommendation systems utilize both Google Plus and Twitter to conduct recommendations on the YouTube site. And so the accuracy is quite high. And for existing users also, since they use additional information about users' preferences, they are able to provide recommendations with higher accuracies. And when it comes to recommendations, accuracy alone is not sufficient to capture the overall recommendation quality. For example, if we identify a user as a football fan, we can continue to recommend him only football-related videos with very high accuracy. But eventually, the user will get bored of the monotonous recommendations that he gets. So to keep the user interested, we should recommend interesting content that are both novel as well as diverse as well. So experimental results showcase that cross-network solutions are able to provide recommendations with better novelty as well as diversity. And it is intuitive as well because cross-network recommendation systems can capture user preferences from diverse perspectives coming from multiple different social networks. Also, despite the added complexity, they were very robust against changes in user preferences, as they were able to quickly update the underlying model using new user interactions with minimum iterations in online settings. And so far, I talked about general limitations in conventional recommendation systems and how to overcome them using cross-network recommendation solutions. So, although this seems a very viable solution, there are still some problems associated with coming up with cross-network recommendation systems. So with that, we will look at the specific research problem that we address in our work here. So far, we showed that cross-network recommendation solutions are feasible, effective, and even practical to be used. And they improve the overall recommendation quality in various aspects as well. So does this mean that we can go ahead and replace the conventional single network-based recommendation systems using these cross-network solutions? Unfortunately, we are not there yet because we still have to overcome this data challenge. That means all the existing cross-network solutions need users to be overlapped across networks. For example, if we plan to conduct YouTube recommendations, we need to know their interactions on at least one other source network. However, majority of the users are non-overlapped. That means although they might be engaged with other networks, we do not know or have access to their accounts on other networks. We call these users as non-overlapped users. So in this case, cross-network solutions cannot be applied to these users. And we have to rely on conventional single network-based solutions which are inferior. Also, this is a generic problem in any cross-network solution, not only cross-network recommendation systems. Therefore, as a solution, we propose a generative adversarial approach to synthetically generate the missing user preference data on source networks for non-overlapped users. And the approach is to learn a mapping from the target network to source network preference manifolds using the non-overlapped users. So we learn the adversarial generation process using three types of data. First, we use matching source and target network data. We consider an overlapped user and take his interactions on both networks within a given time interval. These are vector representations of their interactions. Here we use topic modeling to capture the topics associated with each of their interactions. For example, topics of his tweets or watched videos. Once we have this information or inputs, we use dedicated encoders for each network to learn corresponding dense embeddings. We do this to reduce the sparsity of the inputs and to make the learning process easier. Then these inputs are fed into a component called discriminator, and the discriminator here has to take two decisions. If the given inputs are real data and if they are matching data. Both of these are true in this case because it is taken from a real user and both the interactions happen within the same time interval. And so in this case, discriminator should correctly identify these as mapping data. Next, we use synthetically matched data. Here we use a non-overlapped user. So for them, we only have their interactions on this target network. So again, we use a target network encoder to transform the inputs to dense embeddings. But here, additionally, we have a component called generator. And it generates a new set of embeddings. And the goal of the generator is to replicate the missing source network embeddings for the user. Once we have this, we again feed them into the discriminator. But this time, since these are not real data, but rather synthetically generated ones, the discriminator should correctly identify them as unmatching data. So here is where the adversarial learning takes place. The generator tries to generate more real-like embeddings to try and fool the discriminator into believing that they are real data. And the discriminator tries to somehow distinguish between the real versus synthetically generated ones. So as we train with more and more data, both of these modules, the discriminator and generator, will become more powerful as we train with more data. And but training a discriminator only using these two types of data is not ideal because, as mentioned, the discriminator has to decide two things: whether the inputs are real and whether they are matching. But from these two inputs, it only checks for the authenticity of the data, not the matching part. So to support that, we use mismatching real data. That means we provide data from maybe from two different users or from the same user at two different time intervals. And in this case, since these are unmatching data, the discriminator should correctly identify them. And so it helps to make a more effective and powerful discriminator. That means the generator will also become strong as well, since they learn in an adversarial manner. So now let's look at how to optimize this process. This contains two loss components, the discriminator loss as well as the generator loss. The discriminator loss function has three subcomponents. It is a maximization with the three subcomponents corresponding to the three scenarios that we discussed. LReal corresponds to real matching data and it is log dxy. Here dxy is the probability of the discriminator identifying the given inputs as mapping inputs. So given real inputs here, D tries to maximize the output probability. But for the other two cases, with synthetic and mismatching data, discriminator tries to minimize the output probability that it gives. So it is 1 minus log dxy. And the generator loss component or the function has two loss components. The synthetic loss component is trying to get the maximum probability from discriminator for generated one. So it tries to fool the discriminator into giving a higher probability value. And additionally, we have a content loss function here that we did not discuss in the previous slide. Here, although we have the source network embeddings for overlap users, we anyway generate source embeddings for them using the target network embeddings. And the loss function is to minimize the difference between generated versus synthetic source network information. So the overall loss component is a minimax game, which is a combination of both of these loss functions. So far, we discussed about how the missing user preferences can be synthetically generated and how to train the generation process. Once we have a well-trained generator, we can generate those missing preferences, and we need to feed them into the recommendation process. Here, we look at how the recommendation is trained. For that, we use a pairwise learning approach, where each training instance is a triplet with two users U and V and one item I. The user U has an interaction with item I and V does not. Accordingly, we need to make two predictions, one for each user. And the recommender should try to have a higher rating value for user U and lower rating value for user V. Now let's look at the recommendation architecture. First, we generate the missing preferences for user U. So we have his source and target network preferences here. Additionally, we also use his previous interactions as well because it encodes users' overall preferences. Then we use a neural network architecture to obtain current user preferences based on these inputs. Then we also learn an item embedding as well. So once we have this item embedding as well as the user preference vector, we take the inner product between these two to get the predicted value for user U. Similarly, we carry out the same process for user V as well. And once we have both these predictions, the optimization is to maximize the difference between the predictions so that the prediction for user U will get higher and the prediction value for user V will get low. So far, we discussed about two tasks. The generation task, which has two components, the generator as well as the discriminator. Then we discussed about the recommendation task. Both these tasks depend on each other. First, the generated user preferences are directly used for the recommendation task. An effective generation process helps output quality recommendations. Then the recommendation errors can also be backpropagated to the generator to try and fine-tune the generator into providing more effective generations. Therefore, these two tasks depend on each other, and we learn these two tasks as an end-to-end process in a multitask learning environment. So now let's look at some experimental results. To test our architecture, we created a YouTube recommendation system using Twitter as the source network. And these are the dataset stats. We have over 2,300 users, over 12,500 YouTube videos, and over 2.8 million tweets. And to check the recommendation accuracy, we use both hit ratio and NDCG metrics against multiple top 10 values. Top 10 here means we recommend top 10 items that the user would most likely interact with. Hit ratio directly computes whether the recommended items are consumed or not. So higher hit ratio means that the recommended items are often consumed by users. But NDCG metric considers the position of the correctly recommended item as well. For example, if a successful recommendation is at the top of the recommended list, NDCG value will be higher. And even if we correctly recommend an item, but if it is towards the low end of the recommended list, NDCG value will be low. We tested the recommendation accuracy against multiple baselines, but for the most effective comparisons, we can look at the top 3 of these results. The blue line considers all the users to be non-overlapped and uses only the available target network information. And red line indicates our approach. Again, we consider all the users to be non-overlapped But this time we use the proposed generation process to generate the missing source network references, and then use both real target network information as well as the generated source network information for the recommendation task. So the comparison between the blue line and the red line shows how much of an accuracy improvement can be obtained by generating the missing preferences. And the black line considers the same set of users as overlapped users and use both source as well as target network real data. So this is like the gold standard that we need to reach. We need to come as close as possible to this line. So far as the first step or the first attempt to generate the missing preferences, I think we have obtained considerable step towards this line. And also the diversity and novelty measures showed that the proposed approach could get closer towards the gold standard. And to recap, here are our main contributions. We introduced the novel task of synthetically generating missing user preferences for recommendations. And then we proposed a new GAN-based architecture with new generator and recommender loss components and trained them in a multitask learning environment. With that, I would like to conclude my presentation. If you would like to know more specific details of this work, I have cited the paper here. And finally, thank you very much for attending the talk. And if you have any questions, you can ask now. Thank you.